Good. Set up. Yeah, thank you so much. And thank you, Anton and Florian, for the invitation. And being here is really great to address this workshop. I'm learning a lot of things too, so it's super interesting for me too. And thank you, everybody, for sharing so much. I'm going to talk today about molecular light emission in different contexts, some with statistics, some with vibrational pumping and this kind of things. Before I run out of time, I want to acknowledge people in the group, particularly Ruben Esteban, Adrián Delgado, and Javier Aizpurua. And then collaborations, so that I don't forget, theoretical ones on the top with Nikolai, Thomas, and Getha. They were former members of the group who are now in positions. And then a lot of experimental people, because I will show a lot of theoretical approaches, but also a strong tie with experiments, right? And we have experiments from Gilad, and Weissman, Guillaume, Strasbourg, Saint-Chaudon in Hefei. I won't have so much time to talk about all the experiments, but then, very importantly, Brahim Lunis in Bordeaux with the correlations of pairs of molecules, and Jeremy Bomber for the optomechanics, okay? So what we do in the group is a theory of nanophotonics group, and one of our characteristics, I would say, is to mix a little bit of theory in a versatile way, right? So depending on the problem we want to address, we adopt different methodologies, and of course, this is very reductionist in this chart, but it expresses pretty much what we do, right? So if we are more focused on actually what happens to the matter or to the molecules or to the 2D system we want to address, we solve Maxwell equations with a convenient quantum chemistry description of the polarization or the current. We embed it in Maxwell equations classically, and then we solve surface-enhanced spectroscopies, couplings, and so on. When we are more interested in nonlinear effects derived from the cavities and the metallic gaps and charge transfers, then we go to time-dependent Schrödinger equation solution, and that we can address, as I say, charge transfer effects with molecular and levels in between the pool of electrons, right? So it's very powerful. But these are mean field theories. When we really want to address statistics of light emission, non-classical light, then we have to quantize these electromagnetic fields in gaps and go to master equations, solutions master equations with dissipation, Lindblad operators, and so on. And that's what I'm going to focus today on, okay? But we do all the rest of things. I will show a little bit of the top, too. And I'm going to try to devote like 9 minutes to each of these 3 topics, right? Single emitters in nanocavities, interacting emitters and their statistics, and a little bit of molecular optomechanics. So for the first thing, I think Johannes Feist gave a really good introduction about how molecules are very interesting. They can behave as single quantum emitters, tunable, on-demand, and distinguishable. And on top of that, you can embed them in transport properties with cavities to modify the properties, etc. But paradoxically, there is relatively little work on single molecules, qubits, and their interactions, right? This has been introduced by you, but again, a hand-waving picture. We have an exciton in a molecule, in a typical quantum emitter, 2-level system, and an optical mode that when they are in the weak coupling regime, because the interaction between them is slow enough so that the decay of both is faster, then you just have a parcel effect, an acceleration of the decay, but no real change of the energetics. In a strong coupling, of course, we all know that the coupling goes faster than the losses, and that establishes new polaritonic branches, the lower and upper, and this has the consequences we know in the emission spectrum. Weak coupling is a broadening parcel effect or a split with Rabi oscillations in time, right? So this is canonical, we all know, and people have been exploring these excitons in molecules in nano cavities, either closed or open, for the last years, right? We have seminal works by Litze and Beleza. We have even going statistically to the single molecule strong coupling by Jeremy Bomber there relatively late recently. And in the last years, there has been like an explosion of works putting molecules and quantum dots in metallic nanoparticles and nanoantennas and trying to reach a strong coupling, right? Both in absorption or scattering and in fluorescence, right? I'm sorry if your name is not here, but it's complicated. There was no more more room, right? You tell me later and I add it. So what I wanted to show you some of the work that we did with single molecules, right? Really single molecules. And for that, a wonderful capability, experimental capability, is the tunneling microscope. Because the tunneling microscope is a natural metallic insulator, metallic cavity, a very good nano trapper of light with very low effective mode volume. The top tip, metallic tip, would be one of the particles, the substrate would be the other particle, and the gap in between traps light. You can put one of these organic molecules with a well-defined exciton and try to move the tip, and this is work done by Sen Chaudong in Hefei experimentally. So you see there, this doesn't mark, so I have to do it a little hand waving, right? 3, 2, 1. When it's 3, is far from the molecule, so you just have the emission from the cavity itself. This is a typical fluorescence emission, photoluminescence of a metallic nanocavity. You see how broad it is because it's a lossy cavity, it's metal, right? Very bad quality factor. And when you're on top in position 1, the molecule is just right there, and then you have the excitonic emission of the molecule broadened by the Purcell factor of the cavity, right? But something very interesting happens when you put them a little bit in between in position 2, because then you have this interference between the cavity and the exciton, and you see this funnel-like profile, which is very beautiful. It's interference of the two, right? This is a fingerprint of weak coupling, by the way, okay? Because if you have the broad continuum and the more defined fine structure, you are coupling, you are not splitting, and there is some kind of terrain in between where sometimes you don't know if you're in strong coupling or weak coupling when these branches start opening, but here is clearly weak coupling, right? So we are here interacting, but not strong enough. And the reason why is because the exciton is aligned parallel to the surface and the local field is perpendicular. And the coupling strength is the scalar product of the field acting on the dipole mode. And then the scalar product is quite orthogonal, and the coupling is weak. So for some reason, for some time, we were trying to align this better, right? This is actually, by the way, a scanning of the metallic cavity on the molecule. You see how the funnel-like emerges. You can do couples harmonic oscillator theory, and you reproduce quite nice. Not only the contrast in luminescence, but also in the position of the lamp shift. The lamp shift is the real part of the Green's function there, of this dipole, and we can reproduce quite nicely. As I say, we are all the time in weak coupling, and because, Gary, you asked yesterday about what happens when these picocavities and when the field is super localized, right? In a standard cavity QED, cavities trap light, but they trap it in a very homogeneous extended area, right? So you put your dipole, your exciton, your two-level system, and this two-level system typically suffers an homogeneous field. And when you want to address the emission of this two-level system, you will have the broadening Purcell factor and the energy shift, the lamp shift, and you address them typically by the imaginary part of the Green's function and the real part of the Green's function. But, as you asked yesterday, when we have this type of extreme cavities, like for instance an STM, what you produce here at the tip of the STM is an extreme confinement of light to the almost single atom level. It's what we call a picocavity because it's sub-nanometric effective mode volume, right? And then the field is extremely homogeneous, and the trapping of the effective mode volume is smaller than the size, the actual physical size of the two-level system. So there you need to start taking care of the structure of the dipole. It's not a two-level point dipole. You cannot do the Green's function of a point dipole anymore. So then what you need to do is to extend the point Green's function description and then make a kind of convolution, both for the real and imaginary part, or even for the intensity, of the electronic density of a state expressed in a space as a function of R, and the plasmonic or the local field also. So you do this convolution in the whole effective mode volume, and you can address, for instance, this kind of experiments on this tyrosine. You have this the experimental peak width, so this is mapping with sub-nanometric resolution. A nanometer is something like this. So this is really sub-nanometric resolution, experimental peak width, so this is mapping the Purcell factor, and then when we do this convolution of the local field at the single atom by the electronic transition density, we can reproduce very nicely. Also, the lamp shift with a little bit of a Stark shift, but then you can reproduce. So this is actually what you need to do beyond the point dipole if you want to address the quantum chemistry of a very localized field. This goes beyond point dipole level. As I said, we are in weak coupling, and we try to lift the molecule so that we could align the field here at the cavity with the dipole orientation, right? And Guillaume Schul in Strasbourg, with this PTCDA molecule, is what to try. They are very powerful manipulating with STM. They pick up this PTCDA, they lift it, and then they try to measure that, right? And that's the result compared to the molecule lying down here, which is very thin. You see how good quality factor is, 2.6 millieV. You go to the lifted, and yeah, you see the Purcell factor enhanced with separation layer or without separation layer, but you don't really go to a splitting and a strong coupling, right? And the reason why we did the calculation with Javier in my group, and he did the coupling rate calculation of this kind of situation that with the molecule, this is a trion, this PTCDA is the trion, what couples. You do the calculation with the local fields around the picocavity, lying down or standing up, and you see how standing up, yes, it gives like one order of magnitude, which is compatible with the experiment, but it's still in weak coupling regime. And the reason is that even if you align better the dipole, you retract the tip, so you lower the actual magnitude of the local field. So you gain in alignment, but you lose in local field trapping there compared to the right. Anyway, yeah, I'm going to... But there are situations where you can get strong coupling at the single quantum emitter in plasmonics. If you go with quantum dots, I will go very flashy on this. With Gilad in Weizmann, we did this, right? They put this quantum dot on the bow tie. They have the plasmonic bow tie on the one hand, emission is scattering, the emission of the cadmium selenide zinc sulfide quantum dot. When you put them together, they could measure both scattering and photoluminescence, and they could see the splitting of typical of strong coupling, but both were kind of different. If you put them both together, and you actually also do coincidence measurements, Humphrey, Brown, and Trees experiments, you put them together, you see that they don't quite match scattering and photoluminescence. It's double peak, but they are different widths, different positions. In the correlation, yeah, you have anti-bunching, so it's single photon emission, but it's not, the lifetime is about 11 nanoseconds, which is not compatible with this a strong ultra-fast lifetime that one would expect, right? So there's something fishy. So what you have to do is sophisticate, in this case, this point description two-level system, and the typical situation would be like a James Cumming Hamiltonian here in red, right? You see a dagger, G, A, B, and then A, G. So you see, this is a ground state. You see the bright coupling to a two-level system. What we had to figure out after many, many trials is that you need to introduce another state, a dark state, that is not completely dark when it's in the bow tie. It has a GD, which is much more smaller than GB, but it still plays a role in the dynamics. And when you solve the whole master equation with the Lindblad operators and so on, you actually recover that the photoluminescence and the scattering show very different widths, very different positions, but actually that peak on the left in red is the dark state emission. It's not a strong coupling splitting. And in the correlations, you see that in the theory, we can split two regimes of time, right? One nano scale and another more femto, which is not resolvable experimentally. So everything is right. So this I show you to see that sometimes the two-level system is not enough, either because your field is even more localized at the point dipole, or because you have more states that mess up the two-level simplification, right? More things, going back to molecules. What happens when molecules interact? I have shown you, and Johannes Feist also shown the interest of working with molecules in the sense of quantum emission, photostability, indistinguishable photons, etc. We have very high collection efficiency. Brahim Lunis in Bordeaux works with this type of organic molecules. In particular, for the experiments I'm going to show you, they are working with this DBAT, which is a derivative of this naphthalene. And this is on top the kind of a structure of emission that you have. You have a very clear zero phonon loss, a zero phonon peak, which is very clear, and that's why people describe this system's emission as a two-level system. But very importantly, you have a lot of a Stokes-shifted emission. Okay, this is red-shifted emission, and in these molecules, this is very important, right? I will say in a second. So, in principle, most of the descriptions rely on this two-level system that we all are familiar with. You have very, very nice spectral emission with very low losses, 20 megahertz. And then you can also have intensity correlation measurements that show you the anti-bunch. So it's really single molecule source, right? This Brahim Lunis with Michel Orit had worked out since 20 years ago, right? But now the next challenge was to try to start coupling these emitters, just to try to get entanglement, to try to play for quantum information, right? And people have been doing this, but in nanoscale photonics, this is kind of hard, right? There have been attempts in different cavities, plasmonics, photonic crystals. What I'm going to focus today is in this capacity that the group in Bordeaux has to put these derivatives of naphthalene together. They don't have so much control on how close and how they are orientated, but they just search for them, and when they find a pair which matches well in direction and proximity, they start checking a spectroscopy and correlation measurements, right? So we want to address this coupling. This is a kind of biexcitonic description, a two-level system here. If it's not interacting, you will have a typical spectral response of two-level systems. If there is a little bit of detuning here between omega 1 and omega 2, you would have this little double peak with the detuning. What happens when they start interacting is this is kind of biexcitonic situation. Many of you might be familiar with it. You couple via Coulomb interaction. This is dipole-dipole interaction. That's the kind of Coulomb interaction, dipole-dipole. It's combined with the Debye-Waller-Frank Condon factor, which tells you how many of the emission is Stokes-shifted. But that's the energetics of the system. That's the important thing to get, right? So you create, thanks to this dipole-dipole interaction, hybrid states, right? And you have this super-radiant state and this sub-radiant state, right? And the shift between them is basically given. There you have the formula by the Coulomb interaction and the detuning, right? So if there is more Coulomb interaction, if the molecules are closer, you will have more detuning between the super-radiant and sub-radiant state. But pretty much that's the situation. And when you do the spectroscopy of that, then you can obtain this 3 peaks level, right? So you have the super-radiant emission, the sub-radiant, you can see actually the widths, super-radiant, sub-radiant, and the two-photon emission as well, right? So that's a typical thing that experimentally they see. They, as I say, they find this couple of molecules, they saturate with excitation power, and this structure of energetics is what they see in the experiments. And depending on the configuration, if it's J, dipole-dipole aligned, or H, with dipoles parallel, you have actually reverse of the super-radiant and sub-radiant, okay? Yes, I'm going fast, but it's easy, right? So actually you can do almost metrology, right, from the spectroscopy. You have in the non-interactive system, when I have 2 molecules separated 50 nanometers, for instance, I have a certain 3 peak emission structure, but if I put them closer, the peaks are more separated. If I put them closer, 25 nanometers, so we are talking 40, 25 nanometers, it's very controllable. You see how they split, right? You can see actually, and they measure lifetimes, and you see how is the super-radiant, the sub-radiant emission, you can see directly from the decay, right? All this is a spectroscopy, fluorescence spectroscopy, but what we were interested now was in addressing the statistics of this light emission. How can we play with these interacting systems, right? And again, this is the energetic structure of this biexcitonic interacting structure. And now what we do is correlation measurements. We address the second order correlation of this emission, and we tune the laser for the 3 different situations we might have. We tune the laser to the 2-photon emission, right, omega 0, or to the super radiant or to the subradiant state. And we calculate the correlation, the second order correlation of this emission, okay? And these are the results by Adrian in my group. Recently, we have that if you tune for the 2-photon emission as a function of the intensity of the laser and the detuning is quite homogeneous, but you see that you have a strong bunching, so the emission is in cascade, right, until you get to a saturation intensity where you have the Poissonian emission, right? But if you tune to the superradiant state, then you see a strong anti-bunch emission, right? The same as a function of intensity, laser, or the tuning, and you can see how you can have this anti-bunch emission. Actually, the superradiant state and the ground state behave as a 2-level system, almost isolated, okay? But very interesting, and this had not been explored, is the complex behavior of the subradiant state. This subradiant state shows a background of anti-bunched, but then, depending if you start mixing and interfering with the superradiant state, then start appearing bunch situations. What we have done is also check frequency resolve intensity correlations. Johannes Face showed this, the work of Elena del Valle, who introduced this method to calculate detection for certain omega 1 and omega 2, a 2-level system mimicking the detectors. We introduced that to calculate this, and this allows us to calculate the second order correlation as a function of frequencies of the photons in each of the detectors, right? So you can see how, compared to a standard spectroscopy, we have the horizontal and vertical lines, that's fine, where you have these spheres of Poissonian versus the anti-bunching. But very importantly, in the statistics, you identify these diagonal or anti-diagonal features, which are connected with virtual transitions, which are completely missing in the standard spectroscopy, right? So this kind of frequency resolve correlations is very interesting to do, and I think we would encourage experimentalists to try to go for it. If you increase the intensity, then you open the Molo triplet, and you can see more complex structure of statistics. So actually, you can have, with the intensity of the laser and the detuning, with the Stark effect, the possibility to tailor the statistics of this pair of emitters, right? I think I'm going to skip this, but it's very interesting. They can measure, of course, for each of the emission lines, the statistics. And one of the problems was that most of the times, this statistics has been addressed as a 2-level system. And as I say, in the experiments, they filter the emission for the correlations for the Stokes-shifted photon. So what we had to do is to try to address the second-order correlations of this emission, but introducing, in our theory, an extra level which expresses the vibrational state, and then calculate through the field operator, either if you express the field operator to the vibrational state or to the ground state, this allows us to address the zero-phonon line statistics of emission or the Stokes-shifted. And then we solve the master equation for this Hamiltonian with the addition of this extra vibrational level, mimicking the Stokes-shifted, and that we can calculate for the 3 tuning of the emission, the correlations of the Stokes-shifted. And actually, you compare with the zero-phonon line, for certain situations it's almost the same, but here you have that for the superradiant and for the subradiant, the zero-phonon line statistics and the Stokes-shifted statistics addressed as we are doing is completely different. And when you superimpose the experiments by Brahim, you can see that it's very, very critical to put the Stokes-shifted statistics correctly with respect to the zero-phonon line, okay? This is just a couple of weeks old in PRL, but it's very nice fine-tuning engineering at the theoretical level of the Stokes-shifted emission. I think because I have 5 minutes left that I'm going to skip the rest of this interacting thing. We address or we check where were differences coming in these correlations from coherent part, coherence of the fields, coherence of the diagonal elements. I'm not going to have time to go through this. I just wanted to tell you that this scheme of pairs of interacting molecules could be, and actually this is also about to appear, as a scheme to produce entangled photons. So if you put perpendicular dipoles, molecules on a flat surface, and you have the emission on opposite sides in Alice and Bob, and you post-select in omega, you can get polarization entangled states, like this kind of a scheme is giving you the polarization. And then when you actually calculate the concurrence or the fidelity, you see that you can have, for certain widths of your detector, very nice fidelities and concurrence without losing too much photons, actually. You might have 5 or 6 photon pairs per second. So this could be a very good scheme for entangled photons, right? And in the last 4 or 5 minutes, I wanted to flash another thing we do with molecules, which is a completely different research line in my group, which is about vibrations, okay? And coupled vibrations with cavities, and nanocavities in this case. So we know from classical standard optomechanics that when you put light in a cavity and one of the cavities is connected with a spring oscillator, you can have this radiation pressure that produces a feedback action, and this can be expressed through an optomechanical interaction, right? We are talking here on oscillating kilohertz frequencies and so. What we recently, about 6-7 years ago, realized, the group of Kippenberg, my group at the same time, addressed that SERS, surface-enhanced Raman scattering, vibrations of molecules in a cavity, has an analogy in terms of the energetics and the Hamiltonian and the interaction with this optomechanical situation. In other words, that surface-enhanced Raman scattering is an optomechanical process. It can be described as an optomechanical process. But of course, the frequencies are huge, 6 orders of magnitude more, or 8 orders of magnitude more. So what we started to do is to adopt all the Hamiltonians and descriptions at different levels of linearization and so on of optomechanics to address this molecular optomechanics or molecular nano optomechanics situation. You use exactly the same Hamiltonians with the interaction there, which on top on green is the optomechanical interaction. The single photon optomechanical coupling is basically the derivative, how the energy of the cavity changes with the displacement. That's derivative is the coupling pretty much. And this scales with the inverse of the effective mode volume, right, of the cavity. Now, if we go to a nano cavity, we can do the same, adopt this interacting optomechanical Hamiltonian, and calculate that the optomechanical coupling is proportional to the Raman tensor, and again, inversely proportional to the effective mode volume. Since in nanocavities, this effective mode volume is really reduced, and even more in picocavities, this optomechanical coupling in the nanoscale has the capacity to increase a lot, right? So we are facing a situation in optomechanics, if we plot the losses of the cavity and the optomechanical single photon optomechanical coupling, we are, compared to a standard optomechanical situations of microresonators, cold atoms, in SERS, we would be in a completely different regime of optomechanics. We are much, much higher optomechanical coupling because of the effective reduction of volume, but we are also here because metals are very lossy. So you gain and you lose in this trade, right? And what we have done actually, if you try to do the picocavity in a layer or in an STM, then you can even push that further, right? So what we have done is basically adopt all these tools of optomechanics, calculate the emission spectrum, but now the parameters are the parameters of our nanophotonic cavity, our molecular vibrations. You map the values to these optomechanics, and we can calculate the Stokes and the anti-Stokes as a function of pumping, laser intensity, and then we identify that there is a thermal regime where the pumping is small. So basically, for the Stokes and the anti-Stokes, is the thermal regime what determines everything. But after a certain threshold of pumping, the antistokes start being nonlinear and quadratic because of the pumping and the back action, right? And this is actually something that was identified in this experiment by Jeremy Bamber. It's a metal particle on a metal surface. The molecular layers are in between. And what happens in this is the molecule, biphenyl 4-thiol. And what happens in these molecules when you illuminate is that you produce naturally a picocavity, because you put the energy there, and actually the metal is not something rigid. The metal is quite a soup that comes up. And this is a picocavity. Around that atom, you're going to create a single trapping of light that is going to produce in the Raman spectrum of that molecule certain pico features there, which we actually have characterized as connected experiment and theory that this is connected with atomic scale hotspots localization, and we have mapped them one-to-one, so we are pretty sure that this is the emergence of these picocavities, and then, as I say, this brings you up there. What does it mean? That if you locate yourself in the Raman spectrum on those pico features, and you can start modifying the intensity, like there, in those particular features, you can map the Stokes and anti-Stokes with the phonon population experimentally, and this maps exactly the kind of prediction that we had there. So you actually identify with the picocavity trapping the effective mode volume, the optomechanical action on a single biphenyl molecule there. I'm done. I just wanted to tell you that since then, 7, 8 years ago, what we have started doing is exploring a variety of effects of these molecular optomechanics. Among them, all of this. Resonance airs. So we are coupling actually not only the photons to the cavity, but now we can have also excitons. This is what is called hybrid optomechanics, similar to the Hamiltonians of the polar and Hamiltonians that we saw the first day. We are addressing collective effects, so now we are summing on all emission and vibrations coupled through the cavity. Very nice collective effects that we have identified experimentally as well. It's very hard to do, but we are also identifying optical spring effect, the smoothening, the softening of the energy of the vibrations due to this pumping and to the optomechanical effect. We have identified statistically, and now with the group of China and Hefei in a single molecule, unambiguously. It's amazing. We are just about to submit, and it's really beautiful. And the same way we did the biexcitonic correlations and frequency resolved correlations, we can do the same with optomechanics. Stokes, anti-Stokes correlations, frequency resolved, and that's also very nice. And with this, I think I'm done. Let me just jump to the last, because I knew I didn't have time to work on all this, but yeah, no, but most of them are hidden. So, and that's pretty much the summary of the thing, right? So I just went quickly through emission in cavities of molecules, interacting molecules statistics, very rich, a lot of experiments to be done there, and then a lot of new options also in molecular optomechanics. Thank you so much.
Yeah, thank you very much, Javier. We have questions here first.
I think if you can hear me, in the case of the coupled molecules, when you have, for example, the subradiant and the superradiant case, and you add the vibrations on top of that, is it, for example, addressing, so that when you have the vibration, it dresses this sub and superradiant state, or you have actually sub and superradiants that are created from the vibrational state, if you see what I mean?
No. Yeah, no, the description, how we do it, and methodologically, and it works, is that you explicitly add one more term, right, in the Hamiltonian, but the decay of this vibrational state into the ground state is so fast compared to the rest that in the end it doesn't affect the dynamics. So it's there to address the transition and the fields that act in the correlations, but it doesn't affect the dynamics so much. So yeah, it's exactly done like that, explicitly. And we have checked that. Yeah.
Okay, one more question. Please go ahead.
He has... yeah.
Okay, regarding the molecule optomechanics part, so Are you operating in a regime where your site been resolved, and are you entering? And is this a way forward to have mechanical quantum state generation?
Oof, that's, I wish, but I wish, and obviously it puts you there, but the problem is that you're dealing with metals. It's just a bad cavity limit, right? So then, I mean, my feeling is that if we manage to get a hybrid cavity with plasmonics localized in the field to get enough coupling, and maybe some kind of dielectric thing that also takes to the good cavity limit, then we might get closer to what you are saying. But yeah, I mean, we are exploring that. That's certainly something to go for.
Thank you. We will also take this because you're simultaneous.
Thank you. Yes.
Shall I ask or not?
Yes, yes.
Okay, thank
He
you.
said yes.
This is a really great talk. Bit of echo. I have two small questions, and the first question pertains to the pico cavity. So when you want to model the electromagnetic field confinement of the pico cavities, do you have a recipe for that in what you were just showing?
Yes, that's very important actually, because from condensed matter point of view, a pico cavity, which is an atom protruding, you might think that it's a source of tremendous null locality in homogeneity. I mean, so in terms of condensed matter, to use Maxwell equations, I would say, as a condensed matter physicist myself, no. But we have an ACS photonics where we compare the Maxwell equation that follows a sharp boundary with the pico cavity and the full quantum mechanical time-dependent DFT calculation, and it really reproduces so well the strength, the distribution, everything, paradoxically. So this is good news for, I mean, I think you need to do this once to know that it works, and now that you know that it works, go and use the Maxwell equations with the protrusion at the atomic scale, because this gives you like a lightning rod effect at the atomic scale. So it's like it's a non-resonant feature, and it just produces an extra. It's not that suddenly you gain 2 orders of magnitude of effective mole volume. It's a factor of 3 or 4. But in Raman, to the 4th power, this is 2 orders of magnitude, so it's good.
Okay.
Yes.
And if I still may, the other small question, you showed it on your slide, so there is also a triplet state, there's also intersystem crossing. Is that also incorporated when you model the total
for the statistics, you mean?
Yeah?
For the statistics, we did the 2-level system plus the Stokes shifted. We got rid of triplets, any other dark complicated state. But I mean, you might claim that in certain molecules that might be super crucial in certain dynamics. For this correlation, it seems to be, I mean, the agreement with the experiment is just putting those 2 ingredients is really good.
Yeah, it's a nasty reviewer question always, right? What about triplets? No. Okay, thank you.
Okay, thank you. Let's thank Javier and both speakers again.
Thank you.